This lecture is on preparation of alcohols and ethers, only from alkyl halides. This is primarily going to feature SN2 chemistry, so everything we know about SN2 chemistry can be applied to these examples. Alcohols can be made from reacting alkyl halide and hydroxide, and we've actually seen these examples before in the SN2 chapter. Hydroxide is a strong nucleophile and a strong base, so it can participate in substitution or elimination reactions. In this case, with a methyl bromide, hydroxide can only do substitution. There are no beta carbons, much less beta hydrogens. And so in a substitution reaction, SN2 mechanism, we end up with methanol and bromide ion. And these reactions move forward because you're replacing a relatively unstable anion, hydroxide, with a very stable anion, a halide ion. In this example up here, we've got a primary alkyl iodide, so ideal for SN2 reactions, and then potassium hydroxide. Sometimes hydroxide will be written just as the anion or as how it will be purchased commercially or found on a shelf as some metal salt like sodium, potassium, lithium hydroxides. So it's important to know potassium has a plus charge. Hydroxide, of course, will have a minus charge. It's an ionic compound. We should be aware of that. In this mechanism, since we have a good nucleophile and a primary alkyl halide, SN2 will be the major pathway. If we want to draw in the mechanism, we know that hydroxide is going to attack this carbon. Stereochemistry is not illustrated here, but we know it will attack from the opposite side of the leaving group. As that oxygen is forming its bond, iodide is leaving, and so we can accurately represent the mechanism just like this. If we had a chiral center, we would observe inversion of stereochemistry. But we're able to get our alcohol product. Now in this reaction, we do have beta hydrogens, so it's important to consider the elimination as well. And so in drawing a separate mechanism, we can look at the elimination. This elimination mechanism, if we were going to draw it accurately with regard to stereochemistry, we would have to spin these groups around, and perhaps I can go ahead and do that. And now our methyl group is just rotated up there. This is not a chiral center. Anyway, but here it describes more accurately the E2 stereochemistry. And this is all old news, just showing how it's applied to these specific reactions. So hydroxide as a base now will remove the hydrogen that's anti to the leaving group. As it's removing it, those electrons are forming this pi bond, and the leaving group is leaving, all in one step. And so we would get an elimination product in this reaction as well. And so we would get both the alcohol and the alkene. Now with a primary alkyl halide, typically the SN2 product is favored. This is just a monosubstituted alkene, so it's not as stable of an alkene product anyway. and the pathway is unhindered to form our alcohol. So we'll definitely get a major product. And so this would be a useful synthesis of an alcohol. If we wanted to react a different molecule with a hydroxide, in this case a secondary alkyl halide, well, now this reaction is not going to work as well, being that it's a secondary alkyl halide that's going to slow down SN2 significantly, and really it's going to increase efficiency of E2 because potentially you can create a more stable alkene. Of course, in this case, we're making the same alkene, but usually the more highly substituted the alkyl halide, the more stable the alkene product in general. So here we don't need to go through the mechanism. But we know that our major product would be E2. You would probably only observe a small amount of SN2 in this reaction because it's secondary. So we can say that the reaction works best with primary or methyl alkyl halides, abbreviated RX. So that's all we'll look at for preparation of alcohols. For preparation of ethers, in general, we'll take an alkyl halide and then react that, instead of hydroxide, with an alkoxide, so a deprotonated alcohol molecule. Which will then give us our stable ether and a nice stable halide anion. Everything involved in these reactions takes into account what was involved with hydroxide. Because in fact these are SN2 reactions with alkoxides as the nucleophiles. In order to do an ether synthesis, you need to have a metal alkoxide. And so now it's appropriate in this chapter on alcohols to see how they're made. And it's simple as an acid-base reaction. In general, you just need a base that's strong enough to remove this hydrogen. And so we're going to use pretty strong bases, and there's some common examples that we've seen before. And all we're doing is this simple reaction. Bases that are strong enough are any kind of hydride salt, so sodium hydride or lithium hydride or potassium hydride. These are really strong bases because we know sodium has to be positive. Since it's an alkali metal, that means hydride is the anion. So H minus, a really, really unstable anion, strong, strong base. Also, what we've seen before, sodium amide. Again, a negative nitrogen. Nitrogen's not that electronegative. Really, really strong base. And so any amide or hydride salt will be able to deprotonate an alcohol. If you have a solution of methanol and you add sodium hydride, which is a solid, immediately you'll get an acid-base reaction occur. And that forms this alkoxide plus hydrogen gas. So it's really most valuable and efficient to use the hydride salts because they make a gaseous byproduct that leaves the system. You don't have to worry about purifying it out. If we start with methanol, the molecule we produce is methoxide, or the alkoxide we produce. If it's the sodium salt of methoxide, we call that sodium methoxide. And this is a general way of preparing any kind of alkoxide. So any kind of hydride salt is going to do this reaction very efficiently, 100% conversion. We can convert ethanol with lithium hydride to lithium ethoxide. And so if you notice in the names, you're dropping the anol and just replacing it with oxide. And that'll work for any alcohol. Down here we have T-butanol. Reacting with potassium hydride. We get one of our bulky bases from the previous material on eliminations, potassium T-butoxide. And of course, each one of these is going to produce hydrogen gas as the byproduct. So that's how we make alkoxides. Now we can see how we can use them in synthesizing ethers. This procedure actually has been developed over 100 years ago, but it's still relevant today. It's called the Williamson ether synthesis, and basically it's defined as reacting an alkyl halide with an alkoxide, and these are always going to be SN2 reactions. So for example, if we have these two molecules, we've got a primary alkyl halide, we've got a sodium alkoxide, good nucleophile, good base. Since this is primary, it's set up to do substitution very efficiently. and so we'll get a substitution reaction occurring. And in this specific reaction, we're going to form diethyl ether. The mechanism for the reaction is just an SN2 mechanism. You'll have to know these mechanisms, but you already know them. Oxygen, through its lone pair, it's going to attack that carbon. The leaving group leaves, giving us our ether, and then an inorganic byproduct. And so this is a very straightforward Williamson ether synthesis. If we add one carbon in, specifically at this position, we make an unsymmetrical ether. And so you should think about what's the best way to synthesize this molecule. Well, there's really going to be two options, and one of them is going to be preferred based on what we already know. And so thinking about this as our synthetic target, we should be able to come up with two different routes. And so there's one route which would involve a secondary bromide and this primary alkoxide, or a route where we have a secondary alkoxide and a primary alkyl halide. The most important thing in determining whether it's going to be SN2 or E2 is the structure of the alkyl halide. And so a secondary alkyl halide will favor E2, whereas a primary alkyl halide will favor SN2. These bases, although this one is a little bit bulkier than this one up here, are not as important as the structure of the alkyl halide. They're both similar strength in terms of basicity. This one's going to be a better nucleophile because it's not as bulky, but the most important factor is that alkyl halide. And so if we think about predicting products here, going back to what we did with SN2E2 chemistry, in this reaction up here, probably the major product is going to be the elimination product. And so we would see this as our byproduct. We would end up with the alcohol. And so definitely no ether. And then bromide ion. Down here, however, with the primary alkyl halide, the major product is SN2. In these mechanisms, I just want to point out I'm not being stereochemically accurate. We're kind of tucked into a corner here, but we know that if this was to occur, this nucleophile would have to come from the back side. Perhaps I can kind of illustrate that with this arrow a little bit better. But unless specifically asked to do that, either way would work for just showing how the electrons move. So here we would get our ether as the major product. To summarize, for any Williamson ether synthesis, which is going to be synthesis with an alkyl halide and alkoxide, you'll always choose the less hindered alkyl halide. important to write this down. Most people remember to pick the side with the less substituted something. The problem is you have to make sure it's the less substituted alkyl halide. And if you remember what's important for SN2 chemistry, that shouldn't be a problem. But if you just remember less substituted, several weeks from now, if you're taking an exam, you might think it's the less substituted alkoxide. So you've got to be particular, and it has to be less substituted alkyl halide. That's important. What I want to do now is just give a couple problems, come up with multiple ways to create the ether, and then pick which one's better, which one's going to work best for doing a Williamson ether synthesis. And we can go over these problems. So basically I want to know how you can make this two different ways and which way is going to be better. So these are our three molecule targets. Work on those and we can work through them.